Welcome to the morning session. It's my pleasure to also welcome our first speaker this morning, who is B.Doyon from King's College, London, and he's going to present us his results on correlation functions in many body systems, Euler, hydrodynamics, macroscopic fluctuation theory, and long-range correlations.
Thank you. So it's a pleasure to be here. I thank the organizers for the invitation to be back in the GGI after quite some time. So indeed, I'm going to talk about correlation functions in many body systems and how one can get information about correlation functions using ideas from hydrodynamics. In particular, hopefully I get towards the end to this new theory that we have developed, something based on macroscopic fluctuation theory and new results about correlation functions out of equilibrium, where we see some long-range correlations which were not seen previously. But so the goal of the theory, the goal of the talk here is to discuss correlation functions more generally. We've seen in the talk of Frank Gurman yesterday that this is actually an interesting subject, that people are looking into that and trying to discover what are the behavior of these correlation functions of many observable in space-time. Now, I'm looking at large scales of space and time, so you have average of many observables at different points in space-time, where space and time go to infinity very large, looking at asymptotics of these things, okay? And this is a bit weird. Okay, sorry, so this is not working so well, actually. Not sure why. If it, yeah. I don't know if we have to do some full screen or something. Slideshow, you think that would work? Does that work? Yeah. All right, thank you. Excellent. Okay, thanks. Okay, excellent. So now this does not work. What should I click on? The screen. Yeah, that'd be also good. Yeah, thank you. Okay, so yeah, so correlation functions in various type of states in statistical ensembles, I'm thinking. So not at zero temperature, but finite temperature, GGEs, or even in homogeneous initial conditions, so out of equilibrium, where you have a position-dependent temperature, for instance, where you couple the Hamiltonian density with some space-dependent temperature. So states, statistical ensembles of various types, and various types of models. It's kind of very general. I don't want to concentrate on any specific model, but for instance, spin chains or one-dimensional gases of quantum or classical particles, field theories. Example is the XX model, spin chain, or model of particles with interactions such as the Lieb-Liniger model, or the hard rod gas that Jérôme Dubai talked about 2 days ago, okay? And I'll be looking at local observables such as the spin at position x and time t, or the density of the gas at position x and time t. Now, this is all very general. I don't want to be specific on any specific model. I want to express general ideas and give examples on various models. And what are these general ideas that one can use for all these type of models, for these correlation functions and all that, where the ideas are based on hydrodynamics, which I will understand in a very general sense. So Jérôme actually was asking in his talk 2 days ago, is this really hydrodynamics? Jérôme, I'm talking about you. Is this really hydrodynamics or is it not? Well, I'm not going to be doing philosophy about that. Any theory that will describe what happened at large space-time for me is Euler hydrodynamics, okay, for correlation function, basically, okay, and it's based on such ideas. So this is the type of thing that we're looking into. The plan is to go in 3 parts. Hopefully, I have time to go to the 3 parts. The first part is very basic thing about linear response theory, connecting a bit to what Frank Gurman was talking about yesterday. Second part is going a bit further than linear response, essentially non-linear response, so higher point functions and fluctuations, some theory we developed some time ago. And the last part is something that is in progress and in preparation, a new theory about microscopic fluctuation theory, which gives you in principle every large-scale correlation functions and large-scale transport fluctuation functions that you would want in principle. Okay, so I start with basic results about correlation functions. there are some basic results from long time ago. So Araki in 69 and Lieberman in 72 told us, if you combine the result, told us that in any quantum spin chain with short range interaction, if you look at any state of the form exponential W, where W is potentially some other Hamiltonian with short range interaction, you look at correlation functions of any local observable connected correlation function. These will always decay exponentially outside of a certain light cone. This is true for every quantum spin chain. Okay? And the velocity there is the decay is controlled by some parameter mu, which you can compute, or at least bound by using the knowledge of the Hamiltonian there and W, the other Hamiltonian you put for the state. Okay. And so correlation function decay outside of this account. Now it may be interesting to see how they decay precisely. That's just a bound, okay? But perhaps more interesting is what's happened within the light cone. So Lieberman and Araki do not tell us anything about within the light cone. So precisely Araki told us about decay in space, and Lieberman told us how to evolve up the way to the Lieberman velocity. Okay. So the only thing you can do in spin chains, at least, is that you can bound the whole correlation function by some amount, but you don't know how it goes. Okay. So there are not so many results within the light cone. This is where the interesting stuff's happening. Now there is some result that we obtained recently within the light cone. It's a relatively weak result. But what it says is that, okay, well, it's bounded, but it's a bit more than bounded. So if you take an observable, any local observable, evaluate its time average within any correlation function, in any short-range spin chain, in any short-range state, which is actually stationary and transition invariant. So within GGEs, for instance, or Gibbs states. Okay, you evaluate the time average of the local observable along some ray, so not necessarily at time 0, but along some ray, so VT, T. Well, that inside correlation function at large time will tend to the ensemble average times the identity. In other words, that will separate cluster out of the correlation function. Okay, that's a completely general result in every quantum spin chain of short-range interaction. So what it is essentially an ergodicity result, time average equal ensemble average result. Okay, now it is valid not everywhere within the light cone, but almost everywhere. So where it's not valid, it's a set of measure 0. In fact, it's a countable set of velocities at most. Yeah, sorry. Well, so the theorem it's a bit of a weak theorem, not so constructive, actually not at all. So I have no idea what are these velocities. I don't know if they're interesting, and I think they probably are interesting. So this is for any models, at most there will be a countable number of velocities where this does not work. So I mean, you can take a very simple model where spins do not even interact with each other. And then the zero velocity is one of them, obviously, right? But I don't know of other models, and I suspect in many typical interacting models, there are none actually. It's everywhere, I suspect. Okay. In fact, it's a bit more than that. You can put any frequency and do the time average with any frequency, and it still works. Okay. So what this means is that there's a lot of loss of information at large time, right? So you do average over time, you lose a lot, right? And it doesn't say much more than you lose a lot, but there's some kind of ergodicity, and it's kind of a many-body ergodicity. It's purely based on the short-range interaction, so extensivity of the Hamiltonian. This is an infinite volume. It's nothing else than that, actually. So what remains? So there's a lot of loss of information. What remains? So the idea is what remains within the light cone should be described by hydrodynamics. So essentially, things go to 0, but how do they go to 0? What are the directions where they go to 0 the least fast? Now that should be described by hydrodynamics. So what we would like to do is understand what's happening within this light cone, and it's hydrodynamics idea that tells us that. In fact, Hydro tells us that the Lieberman velocity is not really the relevant one physically. It has very little to do with what you actually observe in physical, correlation functions. Yeah, questions.
The existence of possible existence of this special trajectory is a bit like in billiards when you have that trajectory are ergodic unless they are periodic.
Yes, something like that. I think yes, it's something like that. I mean, the argument for the derivation of that is based on some projection theorems in the theory of entry operators on Hilbert spaces, and is based on the finite dimensionality of the local space in quantum spin chains, which give you some countable dimensionality or something. So I think what you say is correct. The physical idea is correct, but I'm not too sure then how to relate it exactly to that. Yeah. Other questions? Yeah. Yes. No. So there's no assumption about dispersion or anything like that. Yeah, but probably. But I don't know how to prove anything if I deform the ray. Okay, so the proof works for if you have so why is it works? Because when you have a ray like that, you know, if you do one little step, where you do one little step in space and one little step in time, and that can be represented as a unitary operator, right? So a little step is unitary, one unitary operator. So the unitary operator of space translation and time translation together, right? And then you do that to the power n, and you can use theorem about what happens when you average nth power of unitary operators, and that's what I think. No. Correct. No, doesn't depend on spectrum. Indeed. But so this is an excellent point, right? I mean, the point is that this is physically it doesn't tell you a lot of things. Actually, tell you very little, right? And what you would want to have is indeed the rays part of the spectrum, right? So the physical rays where something is happening. Okay, and there are rays where something is happening, and this is what hydrodynamics will tell us. Now, so the other thing is that I'm thinking about homogeneous stationary states here. So, you know, hydro, then there's no curved, kind of curved trajectories. Things in hydrodynamics will go straight. But so what we would like to have is indeed where are things happening and how correlation decays and all that. Okay, so the question would be. Yeah, so this is really the time average of the observable as an operator, and yeah, this is ensemble averaging. Yes. Yeah. For instance, ground state has big temperature 0. Now this is ground state. Yes. So this will work in ground state with. Yeah, this will work in ground states as well, as long as you can show that you have decay of correlations in the ground state. Yes. Other question? Yeah. Yeah. So. Indeed, so there are ways where there may be ways where it doesn't work. There are simple examples, like if the spins don't interact with each other at all, you know, the ray 0 might not work. In fact, for some frequencies, it will not work, you know, the frequencies of the local Hamiltonian. Okay, so there may be ways where it doesn't work. I would expect in typical system there are no, like interacting system, there are no ways where it doesn't work, but I don't know.
So maybe we use the microphone for the other people.
Sorry, I mean, I'm wondering there should be some additional assumptions, because if I have a regular spectrum, like a harmonic oscillator spectrum, then surely this will not hold.
So there's no more assumption. This works for every quantum chain. So local Hamiltonian, local space is finite dimensional. So maybe your harmonic oscillator is not finite dimensional, so I couldn't do it, right?
Yeah, but just a moment. So if I have a regular spectrum, I have persistent oscillations at all times. It's quantum mechanics.
Yeah. So there will this will be exactly some rays where it will not work. Indeed, yes. But that's what it is, right? So you're right. I mean, obviously you have a local thing that oscillates. It will not. It's not ergodic, right? Yeah. So that's why this is a relatively weak statement. It's not a strong statement. Okay? So it's supposed to be valid for everything. So it's got to be very weak, right? But it's not sufficient for certain things. But yeah, relatively weak statement. Other questions?
Maybe I take the liberty to ask a question, Mr. Chairman. This light cone, for instance, for XXZ, we don't have such a simple light cone picture. We have, say, in the massive regime, we know that we have 3 asymptotic regimes.
Yes, correct. Yes.
So
exactly.
For interacting systems, I would expect that in general, the asymptotics may be rather complicated.
Yes.
Depending also maybe on the operators.
Yeah, indeed, I completely agree with you. So this light cone is actually not physically relevant when you actually do the calculation like you do, and you find various asymptotic regimes. I mean, you will not find the Lieber-Rosen velocity in any of your calculation. You will find other velocities that are smaller than that, indeed. And this is where it's actually happening. And so the question is, and everything that you find non-trivially happening is going to be within that cone, actually, right? So it's going to be within that. And the question is, indeed, can you say something about that, right? So this is very general, not super physically relevant, but still something that tells us something is happening here. Okay. Other questions? Okay, so what can we say? Well, we can say something about, I mean, there's a very simple set of ideas, which is linearized hydrodynamics, that tell us something about two-point correlation function. I just want to go over that a little bit. That connects with actually Frank's talk yesterday. You talk a bit about response, correlation functions being seen as response to some small perturbation. So the idea is simply that if you have a two-point function, connected two-point function, you can see the initial operator there as creating a disturbance. Okay, think about two-point function in some Gibbs ensemble, stationary and homogeneous, right? So the initial operator at 0, 0 creates a small disturbance. That disturbance propagates with some velocities, and these are the physically relevant velocities that you have to find. And that velocity, that disturbance eventually at some later time is at some other point. And if there's another operator there, then you have a strong correlation there. Okay? So along these velocities, there may be many of them, many fluid modes. This is where you're going to have the strongest correlations. Typically, you would expect algebraic decay along these velocities and exponential decay away from these velocities. You typically expect that, okay, in typical system. Now, for this, then to have a whole that you have to do hydrodynamics. So I'm going to just review a bit what actually Jérôme explained in his talk about hydrodynamics. So what you have to consider is the evolution of the conserved densities in the theory. Okay? So for instance, if you have the XX model, what are the conserved densities? Well, sigma 3 is conserved density, the Hamiltonian density is conserved, and there are infinitely many more, right, in the XX model. And they have their associated conserved currents. It satisfies this equation. And the point is that these small disturbance should be, their dynamic is obtained from the continuity equation for these conserved densities, okay? Now, so how do you do? Well, hydrodynamics, you think about an inhomogeneous initial condition, for instance, an initial bump somewhere. And when you do linearized hydrodynamics, you're going to take this bump to be very small, just a small perturbation due to the operator that propagates. But for now, just take it to be just some bump of scale L. Now, L is the scale of the variation of the initial state. And for hydrodynamics, so you can think about initial density matrix of that type where you various generalized temperatures, which vary at on scales L. Okay, and for hydro, you think about the fluid cells, which are scale capital L, much smaller than this curly L, but still much bigger than microscopic scales. Okay? So you have this separation of scale, and that middle one is a mesoscopic scale. That big one is macroscopic. This is a microscopic. Okay? And the idea is that if you were to evolve this density matrix in time, then it will still keep, being varying on large scale. And if you were to take the trace of this density matrix on everything except some fluid cells, so some little interval around Lx, so at a large point, and you take the density matrix at Lt at a large time, so large space time. Okay, what you would obtain is something that is very closely described by some GGE or some state that involves all the extensive conserved quantities of the model, but with space-time dependent inverse temperatures or generalized temperatures. Okay, so this is the idea of hydrodynamics. So you have all the conserved quantities, and then locally things look like they have maximized entropy with respect to all the conserved quantities. Okay. And then what you write for describing the full dynamics of this initial condition is simply you write the continuity equation for the locally averaged densities and locally averaged currents that therefore depend on the local inverse temperatures at space-time point xt. Okay? It's important that this is very much like the microscopic continuity equation that I had written there, right? But it is not the macroscopic one, it's the macroscopic one, and the x and t's that are there are the macroscopic variable. You look at macroscopic distances, and you've done some tracing and some averaging within the fluid cell, and you've assumed maximization of entropy. Okay. So this is Euler hydrodynamics. If you take that in typical non-integrable system, you find conservation of mass and Euler equations. Right? If you take that in the integrable system, you find the GHD equation that Jérôme wrote 2 days ago. Okay, and in fact, it's supposed to be quite general for many body system with short range interaction. Okay? Now, if you want to do some correlation functions out of that, you have to look at how the small perturbation propagate in space-time. It's very simple if you hand wavy argument. All you have to do is imagine that you have your initial condition, which is just a small perturbation of your homogeneous state, okay? And see how that propagates. So you just do delta Q, delta J, essentially. So you imagine now that your initial condition is homogeneous, but with a small perturbation, you know, all these delta beta, small perturbation. Small perturbation localized around some point, okay? So, well, if you do the delta Q, the small delta of that, what you find is dt delta Q, and then here you just have to look at how the current changes with respect to the density. So delta J is delta J with delta Q times delta Q. So what you find is that the propagation equation for this small perturbation is a linear equation with a coefficient for the dx term, which is just something called the flux Jacobian, which is the derivative of the current in GGEs with respect to the densities in GGEs. Okay? And in your maximal entropy states. Okay? So this flux Jacobian is like a propagator for these small perturbation. Okay? And this is a linear equation with constant coefficients because you evaluate your flux Jacobian in the homogeneous state because it's small perturbation over a homogeneous state. And so this easily you can diagonalize it. And what you find is the normal mode, which are just linear combination of these delta Q. And you find that they propagate with eigenvalues or elements of the spectrum of this A. So the spectrum of A is the set of velocities. So this is your set of hydrodynamic velocities. It's the set of velocities that are physically relevant. It turns out, by complete general argument from statistical mechanics, that the spectrum of A always is within the real. So it's our real numbers so can be interpreted as propagation velocities. Okay. So this is the main thing, right? So you start with this equation of hydrodynamics. It's an equation for the local temperatures, but you can also see it as an equation for the local densities because it's bijection between the temperatures and densities via this equation. And you get propagation of small perturbation. And then you can transfer that into an equation for the correlation function themselves because it's a small perturbation that gives correlation. So it's the same equation for correlations as it is for the small perturbation. Okay? So this is a linear equation for correlation functions with constant coefficients. It's actually very simple. So you've reduced the problem of correlation functions of densities to something really, really simple. You just have few of them, well, as many as you have conserved quantities, right? And you just have a linear equation which you can solve relatively easily by Fourier transform and diagonalizing the A matrix. Okay? So you can do that in many systems. In particular, you can do that in integrable system using GHD. So I'm not going to go over all the details of this, but basically the formula you get is rather explicit. So you just solve this equation and all that. And in GHD, what's happening is that the spectrum of A is continuous. So you have a continuum of velocities everywhere. And so you have actually algebraic decay of correlation functions at all directions in space-time for all this. So, but it is algebraic decay, right? So this, of course, the time average of that would be 0. So it's really decay. There's no directions according to this formula where things don't decay, right? And what's the algebraic decay? Well, it's completely controlled by the thermodynamics of the model because in the end, the flux Jacobian, this flux Jacobian is just something constructed out of the average currents and average densities in thermodynamic states in GGEs. So it's just involves things from TBA, from the thermodynamic Bethe-Ansatz, like the density of Bethe roots, the occupation function, some dressing of one particle eigenvalues, the TBA dressing operation, which is a set of linear equation, and some effective velocity that Jérôme talked about in his talk. Now, this effective velocity is the velocity of these Bethe quasi-particle as it goes through a gas of other quasi-particles. So it's a modification of the bare dispersion relation, right? That is due to the state. Okay? And this is the formula which you can calculate. Now, from this formula, what you actually identify is the fact that these effective velocities in GHD are nothing else but the velocity of the propagation of hydrodynamic modes in the hydrodynamics of the integrable system. So they have this interpretation. These are the VFI. You have a question, Paul? Oh, yes. Yeah. 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 Sure. Yeah. Yeah. Well, here Yes. So but here, all I see or all I claim here is long time. Okay, this is a long time, the long time asymptotic of this correlation function. Yeah, but this is, yes, but it doesn't matter. This is not a, so I'm not doing a linear response on the microscopic evolution, but rather linear response on the hydrodynamics. Okay, so you know, I take the hydrodynamic equation and I do linear response on that. Hydrodynamic equation is fine, but I agree with you that my argument is very, very flawed. I mean, it's a hand-wavy argument. There's nothing rigorous in there. It's just a lot of blah blah, right? No? And then I get this formula. But this is supposed to be large time and linear response on hydrodynamics. Okay. Now you can say this is right or wrong and all that, but you can check that numerically seems to work, right? In many systems, integrable systems. Okay. It's been checked, you know, by other methods like finite density form factor expansion seems to work. And you can also do it in X model, seems to work and all that. But I think it is an important point that this is kind of hand-wavy argument, and one can wonder about other effects that are not taken into account here, right? In fact, there's many things that when I write this formula, I hear also, I hear Paul telling me, oh, well, but this cannot be true because, you know, there's all kind of, you know, it's not rigorous, all kind of things can happen, or even Frank telling me, yeah, but this is not rigorously derived and all that. And these are correct things that one can say. So
just one more question. Do I understand correctly that the crucial thing is here that this concerns the correlation functions of the conserved charges?
Yes.
Is that right? Yeah.
Yes.
Otherwise, I would not believe it, but it's true. You're just considering conserved charges.
Correct. This is for conserved charges. Now, if it's not conserved charges, then in general, this is wrong. Yes.
And how about the?
But for some other observables which are not conserved charges, this is still correct, where you have to change this address to something else. And there's a definition of what you should put there for the observable. But sometimes this thing that you have to change for something else, you try to calculate, you just find it is 0. So sometimes for some observable, this gives you no information. For instance, for some observable, the decay will be exponential, right? As you know. And then that will just give you 0. But for some observable, it's not exponential, and that will give you the leading 1/t. So this is the leading order, so not exponential. It may be 0. If it's not 0, that will tell you what it is. So, so there are different kind of problems with this formula. In fact, so I wanted to say you can do this on the XX model for the sigma 3, which is conserved density, right? Sigma 3. But so if you do that, the XX model is very simple. It's free fermions, so the dressing is trivial. You put your H equals 1 in there. Rho is just your density of states, you know, from the Gibbs distribution of free fermions, you know. And V effective is just 4 sine P, you know, in appropriate normalization. So it's very simple. However, this formula in XX model for the spin sigma T is in fact incorrect. So if you do it properly, you take Frank's formula that he wrote yesterday, you do the saddle point analysis, you do not find that. So what do you find? Well, you find, here's some calculation. Well, you find that. So you look at large T on some ray, you find some formula. The first few terms, this is correct. This is in agreement with the kind of TBA form and all that. Okay, the first few terms are correct. But the other term that you find from your saddle point analysis, this is just free fermion calculation, is simple, is some oscillatory term. Okay? And this is not described by this hand-wavy hydrodynamic argument. Okay, so the asymptotic arrow is actually not quite correct. In fact, if you want to correct it, you have is crucially important when you describe hydrodynamic quantities, hydrodynamic correlation function, correlation function from hydrodynamics. It's crucially important that you do fluid cell averaging to get rid of oscillatory terms or any other effects that are not described by Euler hydrodynamics. Okay, so here, if you do indeed averaging over space and time, you get rid of that, and then the result, this first few terms, is correct, is in agreement with the general formula that I wrote. Okay, so fluid cell. So in fact, the correct statement of hydrodynamics is fluid cell average observables at large space time, at large x large t, corrected correlation function is described by this linearized Euler equation. Okay? That is a statement. Now there is, so Paul was complaining about all kind of things that can happen in rigor. In fact, there is a rigorous result that I derived recently. You can write precisely what you mean by fluid set averaging. Okay? So you can, here, the way I'm doing that is by doing Fourier transform with very long wavelength or small wave number that goes like 1/t. And I'm doing time averaging of this whole thing. So two things, right? Taking the limit of large time of all this, okay? Now, this object, Fourier transform two-point function, time averaging, does satisfy, this is a theorem that I showed using methods of quantum statistical mechanics, that this object does satisfy the linearized Euler equation written here in its Fourier transform way. That's true for every short range, every finite range Hamiltonian evolution in every Gibbs states or GGEs with finite range operator in the exponential. Okay? So indeed, it is true. It's not just a hand wavy thing. It is actually a rigorous thing. Now, in this object, there is of course a sum over all the modes that's involved there. And if this is to be rigorous, well, I have to tell you what this sum is. I mean, part of the theorem, this is differentiable in kappa, which is real. And part of the theorem, this sum indeed exists. In part of the theorem, there's also a well-defined notion of what are these extensive conserved quantities. This was also a bit hand-wavy, right? You take the conserved charge of the model, but what are all the conserved charge, right? What is a complete set? Well, there is a well-defined notion of the complete set of extensive conserved quantities that involve in this linearized hydrodynamics theorem. So, and it's relatively simple to do. So I just very quickly, I don't want to go in details because details are not very interesting, but the point is to construct some Hilbert spaces. You look at correlation function, connect the correlation function of any local observable and you sum over all space. So like total correlation function, okay? And this, you think of that as an inner product. It turns out that it's positive semi-definite. So you can take kind of equivalence classes, which are essentially all the observables shifted by any amount of space. Okay? So equivalence classes of that, and then this becomes an inner product. And then you can complete it to a Hilbert space by standard Cauchy completion. And what you get is some Hilbert space of the extensive observable. You can show that the time evolution acts as a unitary operator on that. So this I did show, which involve a bit of calculation. And then you can just define your extensive quantities in the most naive way, just as all these extensive observables that are invariant under time evolution for that unitary operator. And turns out then that this right-hand side of the linearized Euler equation is nothing else but the projection of the current onto these conserved quantities, which is a subspace, a closed subspace of that Hilbert space of extensive observables. So that makes mathematical sense. And this object S is defined on that Hilbert space. So there is a kind of rigorous notion of linearized Euler hydrodynamics. And then what remains to do if you want to obtain the equation from GHD, remain to really understand what these extensive conserved quantities are in an explicit model, integral model, like to connect that to the beta ansatz. Now that for now, this is kind of a formal definition. Okay. Okay, so this is a linearized Euler hydrodynamics. Yeah, so I kind of working on it, and I'm hoping, not yet done, sorry. It's an excellent question, is the thing that you have to do, right? That this should be simply spanned by all the A dagger PAP in your XX model. A dagger PAP, these operators, they will not quite be part of this Hilbert space, but it's a bit like kind of expanding your L2 functions in terms of scattering state, which are not square summable, right? So these are not quite part of it, but you can use that to form element of that Hilbert space. Yeah. Yes.
What do you mean precisely by short range?
So yeah, there's a precise. Sorry.
Maybe you can repeat the question.
So the question, what do I mean by short range expansion? There's a precise definition that you can find in textbook about quantum statistical mechanics, and basically the interaction should decay exponentially. It's kind of precise way of saying what do you mean by interaction decaying exponentially. Yeah. Cool questions.
Just to come back to your point about the XX model, I mean, isn't this really a very simple matter? I mean, so what hydrodynamics can give you is the Q goes to zero limit of response functions.
Yeah. Sure,
and the term you don't capture is the staggered piece, -1 to the n, and you wouldn't expect to get it in the first place.
Yeah, correct. I agree with you.
And that's all.
I agree. I fully agree with you, Fabian. The exact model is completely trivial. I don't need to do all of that, right?
But also you don't expect to get this term by
construction. But actually, so maybe I make a little comment about that.
Right.
So this is a very good question. Thank you. So in this construction, there's a way of modifying this construction to exactly get that term. So that term also is a hydrodynamic term, but I think of hydrodynamics in a generalized sense. Okay, how? Well, I told you about the Hilbert space here, right? In this Hilbert space, you sum over x, and here you do time evolution. And all you need is these things to be in trio operators. Okay, so what you can do is modify your time translation by putting a little e to the I kx. That's still unitary within the GNS Hilbert space of this quantum stat connecting. Okay, and the tau t by e to the I omega t. That's still unitary again. And then the same formulation holds for these modified space-time translation. What you find is that you find the same equation, linearized hydrodynamics, with a different space of conserved quantity that depends on k and omega. And if you choose the right k and the right omega, this space is non-empty. There are things in there. And the projection onto this space, this kind of thing, will give you that oscillatory term. So even that oscillatory term can be obtained by, but it's not yet fully written, unfortunately. Progress. Other questions? Yeah. Sorry? For XX, we wrote something a bit simpler. For free fermion, large time you have oscillation at all directions. Now you can understand that from hydrodynamics in this way that we wrote. And for XX, I wrote it in a talk some time ago. It's not yet in a paper. All right. Okay, so somehow this formal thing is actually useful because it allows you to kind of go a bit further where you didn't think you could go, essentially. Yeah, so okay. So I'm not sure what time it is, sorry. How much time do I have?
You have like 8 more minutes, but I mean, we had a lively discussion, and I think, well, we'll see. I mean, you can probably have a few more minutes.
Yeah, sorry. So
you're interrupted.
I didn't go as far as I thought I would, but maybe I go to the last bit just already, and I come back to that bit if I have time, if questions. I wanted to describe that. So this was correlation function, 2-point correlation function at large scale of space-time. Okay. Now, we'd like to go a bit further and do higher point correlation functions and all that. The bit that I skipped was doing a bit of that, but here is kind of our new theory, which we call ballistic macroscopic fluctuation theory. The idea comes from something that people have called macroscopic fluctuation theory, which has been developed for quite some time. It's very successful, and it has been proven in certain models. Macroscopic fluctuation theory developed for quite some time. That was good for diffusive systems, okay? But here I'm thinking about ballistic system. I'm going at Euler scale, right? So it's slightly different, okay? So what is the theory? Well, I'm looking now at some initial state again of that type, okay? So beta of x over L. So I have kind of a large scale varying inverse generalized temperatures in my initial state, okay? And I'm looking at correlation function, not just 2-point function, but any point function. So this limit is supposed to be the thing that the theory is going to describe, because now this is far from being rigorous. So we think that's the right thing. You put the average over fluid cells there, otherwise, things again don't work. So with average fluid cell, probably it will work. You put some L to the n-1, so this 2-point function at large L decays, and you would expect just from naive counting, Euler scale counting, you would expect that to decay like 1 over L to the n-1. So you take away this decay. Okay. Now, that limit, actually, to be precise, that limit is not necessarily a nice smooth function of x and t. It may involve delta functions and all that. It may be a generalized function. Okay, but in an integrable system, it appears to be a smooth function. So so we take that limit in some sense. Okay, and the idea here is to replace this complicated quantum evolution and all that by a purely classical fluctuation theory. Okay, so what you say, you replace your fluid cell average observable at large space-time by fluctuating random variables on which you put a measure. And the measure should be describing what happens at this large scale. Okay? And likewise, you replace any other observable by some fluctuating observable that is now a function of these random variables. So these A check, this little check, I'm sure if you see very well, but it's not A check are functions of these Q check. How they function? They function simply by taking their GGE averages. Inside the GGE determined by these beta check, and the beta check are just those corresponding to the Qs, right? So there's a bijection between the Qs and the betas in the GGEs, and that's what you use. Okay? So these are now random variable, and you put a measure on these Qs in order to describe any of these constant functions. What's the measure that you put? Well, here's the measure. So dp, kind of mathematical notation. It's a flat measure on the Q, so just product over xt of dqx comma t. So this is a flat measure on all of space-time, okay? And times what? Well, something that depends just on the initial condition, something that specifies the initial fluctuation of this random variable. And that thing is supposed simply to reproduce this initial density matrix. Okay, what is involved? Well, there's the betas of the initial density matrix. Okay, and now the x here are macroscopic x's. I've taken, if I go back here, I've taken the limit when L is large. So this x and t are now macroscopic. Okay, so this beta of x here. There's the fluctuating variable there, and this is the fixed function of the initial condition. So this is just the average of the densities within that initial condition at x. Okay. And here, these S's are just Yang-Yang entropies, it's just the entropy. Okay? So in the integrable system, there's the Yang-Yang entropy that depends on the Q's of the initial condition, and here the fluctuating Q's, the fluctuating Yang-Yang entropy. That thing is just actually a relative entropy between the state corresponding to this fluctuating Q and the actual initial state, the fixed initial state at x. Okay? And the rest is the evolution and evolution. So this actually was known. This is not our discovery. Of course, this was known. It was derived by Derrida and others quite some time ago. And our proposal is that delta function. It's a very trivial proposal, actually. Sorry about that. So what it says is simply that you start with this initial condition and you evolve it simply. So you evolve not just the initial condition, but the whole fluctuations. You evolve them using Euler hydrodynamics. So you write the delta function for the fluctuating Q and the current evaluating at that fluctuating Q. So this is just Euler hydrodynamics for that fluctuating Q. So you have many Qs, they fluctuate, and whenever you have a configuration of Q, we evolve it with Euler. And that gives you the fluctuating Qs in space-time. That's the proposal of this ballistic macroscopic fluctuation theory. Okay. Now, so that is, this limit should be reproduced by that limit with fluctuating variable. This is kind of precise statement. Okay. Now, where does it come from? Well, the idea is separation of fluctuation, separation of scales in the fluctuations. So you have smart, very quick fluctuations. So think about this is like a two-dimensional system. You have a lot of things happening within the fluid cell, and typical observable will be subjected to very quick fluctuations due to interactions between the particles within the cell, right? Things that are not conserved. Whenever you have an interaction, it changes a little bit, right? And that this varies very quickly because proportional to the volume within the cells. While the conserved quantities, well, they just change when you have things coming in and out of the cell, the surface effect, and these are much lower effects. So you have a separation between fluctuation of the quick things and the fast and the very slow thing. And it's that separation that allows you to just concentrate on these slow, more slowly varying, slow fluctuation from the surface effects. And the theory just describes these slow fluctuations. Should be valid just at large time. Okay. So I don't want to go in the detailed theory. You write delta function in terms of some kind of Lagrange parameter field. You take the large L limit. You get some saddle point equation, which are very similar to the standard MFT equations, but here at the Euler scale, they involve the hydrodynamic equation for this beta variable, the beta check related to the Q check, okay? And they involve some other field coming from delta function. There's kind of forward and backward evolution. There's all kind of things happening, but you can solve that in integrable models using normal modes, okay? And you do that, and what you find, one thing, what you find is that this reproduces linear response correctly. and reproduces current gravity fluctuation relation and other kind of large deviation functions correctly. So it reproduces many known results. Okay? But it gives also something new. What it gives is that if you look now at large scale separation, but equal time correlations, you find something non-zero. In other words, this initial density matrix, when you evolve it in time, is no longer of the form exponential beta of x, q of x. Like, in fact, I was kind of assuming that, but it's no longer of that form. So the initial density matrix, which have well separated fluid cells that are not correlated, as you evolve it in time, the fluid cells get correlated. The physical process is that when you have inhomogeneity, you have modes that are emitted simultaneously from this homogeneity and that are correlated and that lead to large scale correlation, even at equal times. So as you evolve in time, the measure that you get is no longer a measure of separate independent fluid cells. Fluid cells have long-range correlations. That's a consequence of analyzing these equations. And you can do some numerics with the hard rod gas, where we look at some initial bump condition. We look at the density of the hard rod gas at large space and large time, both at equal time, though. And we scale the whole thing by the appropriate factor. We do Monte Carlo and then compare with the BMFT formula we get from using GHD. And this agrees very, very well with the Monte Carlo simulation. So this is the theory that in principle describes for you all large-scale correlations. It's a theory based on taking saddle point analysis, and it gives rise to new type of correlations, which, as far as I understand, had not been appreciated before. So when you have this inhomogeneous initial state, you have new long-range correlations that appear.
First of all, so these corrections, they disappear in the scaling limit,
yes.
and so what you're saying is they always scale like 1 over the scaling.
Yeah. Well, so to be precise, I mean, really? No, I mean I cannot claim that. In integrable system is the case, I think, right? In integrable system is the case because you have this constant mode, but not in integrable system. You see. I'm not too sure, I don't want to make big claims that are not correct, right? But when we write this type of stuff, right, that limit is not necessarily a usual smooth function, can be delta function, meaning that actually the scale might not be 1 over L, but 1 over square root of L, right? If you have diffusive or something like that. And then I try to take that limit and I will find infinite there and 0 there, and then that would be a delta function, okay? So it's not necessarily 1 over L, the scale, no. But what you get there might be delta function, whatever, that will represent, if you have something which is not a 1 over L, but something slower, that will be kind of washed out under this fluid cell averaging, and that will be delta function. I will tell you where are the correlations and the total weight of the correlation, let's say, but not the exact scale. But that's a very good point, of course, because it will be, I mean, it is a strong statement to say it's 1 over L. And I think it's the case in integrable system mostly, but probably not in non-integrable system. I'm not completely sure, actually. So completely sure. But here in the hard rods, it does work. Yeah. Other questions? Yes.
You have a delta function in this conservation among rho and j. If instead you put a kind of new fixture temperature parameter, the delta is a tight Gaussian. You have a quadratic part in this new field, capital H.
Yes.
This stable for a while and then makes a phase transition.
No, so very, very good point. So actually, we don't know too much, in fact, about. So this relates to, this thing, right? You want to go a bit further, for instance, like you have thermal fluctuation, right? Well, you would have some h square or something like that if you consider. So I go back here. Say, if you consider not just the Euler scale but the diffusive scale. I think that's what you're getting into. So indeed, you consider diffusive scale. So where the currents is not just the Euler current, but you add diffusion. In this case, actually, you have to also add some noise, and there's an Einstein relation that relates the noise to the diffusion. Okay, and when you do that, you still have delta function, but now you have also fluctuating fluctuating currents because of that noise. Okay? And then when you do with the h, then you can get the h squared, depending how you write it. So your noise will give you some Gaussian thing. Okay? And then so there's an extended theory that will give you that, but we have not fully analyzed it. Now, if you take that extended theory and then get rid of the ballistic part, which is the only thing we're looking at, get rid of the ballistic part, you recover the standard MFT, the diffusive MFT. So in this sense, it's connected to the diffusive MFT, and there is a bigger theory that puts these two together that has ballistic and diffusive, which hasn't really been analyzed yet. But yeah, there will be corrections to that, and I don't know what they are. Other questions? Yes.
So, thank you. Yeah, so why is the inhomogeneity important?
So yeah, good question. So, so the main thing is we have to have two modes kind of being emitted. This is my physical explanation, okay? So the reason is why you do the calculation, and that's what it gives you, okay? But physically, you have to have two modes emitted somehow at the same time. So if you have things homogeneous, there's nothing emitted, right? So it's like linear response, right? When you have linear response, you have to have a bit of an homogeneity, and that produces something, and then you know, that is emitted. When you do linear response, actually you have a sum of modes, right? If you were to do nonlinear response the next term, then you'd have this product of modes, and these modes being entangled. Entangled is not quite the right, but correlated, okay? And so you have to have the homogeneity to produce these modes. And the homogeneity has to be big enough to produce at least two that are correlated. And you have to have at least two different velocities so that two can be emitted and correlated. And in fact, the stem has to be interacting. If it's a free fermion, it turns out that there is no such correlation. Everything is linear in the end. But free fermion is just a sum of modes anyway. Right? So all these conditions have to be there. Yeah, does that explain? It's just physical reasoning. I don't know. Yeah.
Yeah, maybe just go ahead and move towards.
Yeah, that's it. That's what I wanted to say.
Ah, okay, sorry.
Yeah.
I didn't understand.
No. Looking at the time. So, conclusion. So, Hydro gives you a lot of information about large-scale correlation. Some bit is actually more rigorous than we thought. Some bit is not rigorous, but you can, in principle, get quite a wide array of predictions for large-scale correlations. Okay, I didn't talk about the fluctuation formalism and twist field and all that, but there's a way of relating these large-scale fluctuation, for instance, that described by BMFT, to other correlation functions, for instance, that you are interested in, the sigma plus, sigma minus, and XX model, for instance, is not described by linearis Hydro. This gives, you know, because it's exponential decaying. But still, you can use Hydro to describe this exponential decay. It corresponds to a large deviation function of total integrated quantities. It can even be used to describe entanglement entropy. So Laja described in her talk how entanglement entropy is related to twist field, and twist field can be studied using hydrodynamics as well. Okay, there's some work in progress there. And yeah, so there are a few questions there that one might want to answer in future research, in particular in grant applications. Yeah, so thank you for your attention.
Yeah, thanks for this lively talk, Benjamin. We had many questions, but there's certainly time for one or two more, if there are. If not, then I may ask a question. There's who? Sorry, I didn't.
Can you? Hydrodynamics to estimate large deviation function. You have something more or less equilibrium, and you have the time t something weird happens somewhere, and then you react there.
Yeah. So maybe that gives me the opportunity to go back to some bit that I missed. So I'm not sure if it's exactly answer your question precisely, but maybe related. So we can use hydrodynamics to estimate this f, which is, you know, the Legendre transform of large deviation function, as you know, right? So this, what you look at here is the average of a total time integrated current. So that is a large quantity, and that will, you know, has some large deviation. It's something plus some deviation out of it, which happen rarely. Okay? So that should grow exponentially with t with some function f of lambda, and that tells you how much stuff has passed from left to right in time t. Okay? And yes, hydrodynamics gives you that. There's a an exact solution to this problem purely from hydrodynamics, actually. So this f of lambda can be written as an integration over some lambda prime parameter of an Euler current evaluated in a GGE that now flows with lambda according to the flux Jacobian. So what it says is that when you put this current there, you actually change the state to a new GGE. And the way you change the state, you obtain by looking these linear modes, if they go from left to right or from right to left, you know what is their velocities, you look at that, and you modify the betas accordingly, according to that. And that gives you an exact f of lambda for this large deviation. And this reproduces a lot of results that have been obtained in the literature. For instance, in TSEP, there's result by Fabien and Jan de Gier from a long time ago about the large deviation of transport of particles from left to right. And this little equation is very simple to solve in TSEP because it's a one mode fluid. You get exactly the same formula as what they obtain. Of course, they obtain more rigorously. You can also do in the hard rods, and there this GG is complicated formula, but you look at like energy transport from left to right, calculate the cumulants of that, and indeed they agree very well with the numerics. And then in free fermion, they produce Levitov-Vestovic formula. In CFT, it reproduces our formula that has been proven by Kirchhoff and Carol. In a box-bound system, recently it's been shown analytically that our theory indeed produces the right formula for the large deviation function. So yes, there is. Yes, so then still large deviation, yes, so would be related to current fluctuation. Yeah. Yes. A question?
Yeah, maybe at this time it's we should stop and postpone further discussions to the break. And I suggest that we extend the break a bit because we are over time and start again 10 minutes before